Another area where complex numbers is really handy is for proving trig identities, because we can change it into polar form, and we have a sine theta and a cos theta and things like that. Let me show you a few. Now obviously we know the answers to at least I hope, we know the answers to these already. Cos 2 theta and sine 2 theta. You may remember sine 2 theta, I hope, is 2 sine theta cos theta. And cos 2 theta, well actually there's 3 different ones we could have there, but we started off with the cos squared minus sine squared theta. We can use de Moivre's theorem to actually prove this. Because we could say that cos 2 theta plus I sine 2 theta is the same as cos theta plus I sine theta squared. Because de Moivre's theorem says we raise a complex number to a power, we multiply the arguments by that power. So it becomes cos 2 theta plus I sine 2 theta. So all I have to do is expand the right-hand side out and then equate real and imaginary parts. And look what we get. Expand the right-hand side out, we get cos squared theta plus 2I sine theta cos theta minus sine squared theta. So the real part will equal the real part, cos 2 theta is cos squared minus sine squared, and the imaginary part equals the imaginary part. Sine 2 theta equals 2 sine theta cos theta. A much quicker way of proving those results than we saw earlier when we first looked at those identities. But of course this then can be used for higher and higher powers. And finding the formulas for the higher powers, you might remember, was quite involved indeed. Let's try 3 theta then. We can come up with a formula. And let's go the whole hog. We're going to do sine, cos, and tan as well. But it'll start off the same way. I'll use de Moivre's theorem and say, well, cos theta plus I sine theta cubed would be the same as cos 3 theta plus I sine 3 theta. Expanding out. Now, of course, be careful when you're expanding out, because remember I squared is -1, so I cubed becomes minus I, and things like that. Equating the imaginary. Sine 3 theta becomes 3 sine theta cos squared minus sine cubed. Now, if I wanted that just in terms of sine, I could then substitute in for cos squared, and we come up with 3 sine theta minus 4 sine cubed theta. And then equating the real part, cos 3 theta, there it is, cos cubed minus 3 sine squared cos. But again, if I want it all in terms of cos, I'll change my sine squared to 1 minus cos squared, and we get 4 cos cubed minus 3 cos. All right, we set ourselves a challenge here. We said let's do tan as well. Well, tan 3 theta would be sine over cos, and we've just worked those out. So there it is, 3 sine theta cos squared theta minus sine cubed all over cos cubed minus 3 sine squared cos. I want it all in terms of tan. And that looks like a daunting prospect, but actually it's quite easy. All we have to do is look at the highest power of sine. And the highest power of sine, well, mind you, it's the highest power of cos as well, you'll notice. But the highest power is 3. So if I divide everything by cos cubed, because that'll turn the sine cubed into sine cubed over cos cubed, which would be tan cubed. But look what happens to all the other terms. The 3 sine theta cos squared, well, the cos squared cancels with the cos cubed, leaving me with just sine on cos, tan. And in fact, that pattern happens all the way through, you'll notice. So the sine cubed on cos cubed, we were expecting that. On the bottom of the fraction, cos cubed on cos cubed, well, that's just 1. And then I get sine squared on cos squared, that's tan squared. So the key is just look for that highest power and divide by cos of that power. And it should tidy up quite nicely. There's our final answer. 3 tan theta minus tan cubed over 1 minus 3 tan squared. Powers of 4, powers of 5. Once we've done a topic in Extension 1 called the binomial theorem, we'll see a nice quick way of expanding those out. So hopefully I didn't set you ones with too big a power at this stage. All right, let's look at this next example. Show that x equals the cosine of pi on 9 is a solution to this particular equation. Now, show that questions. Of course, a valid way of solving a show that question is to substitute it in and go, oh, look, it works. Right? And that's certainly valid for show that. They're not asking me to prove it. They're just saying, hey, show it works. And of course, another way is to actually solve the equation. So let's do it that way. I'm going to just solve the equation and from that show that it works. But if you do get a nice number, probably why I didn't pick that one is because I don't know the exact value of cos pi on 9. So if I substitute it in, I'm going to go, oh, what's 6 times cos pi on 9? Oh, I don't know. So I can't really prove it that way for this one. But if it was something like cos pi on 3, certainly I'd substitute that in because I know what that is as an exact value. And that would be easy to work out. So all right, we're going to solve this equation. You'll notice I've done a strange factorization. I haven't bothered with the minus 1. And I've taken 2 outside of 4x cubed minus 3x. Now, the reason I've done that is have a look at the answer to the previous example. Okay? And I'm looking for the cosine relationship. And you'll notice cos 3 theta was 4 cos cubed minus 3 cos. And so there's that same pattern, the 4 times something cubed minus 3 times that. So what I'm going to do is I'm going to say, okay, let x equal the cosine of theta. And that will change it into a trig equation. There's that 4 cos cubed minus 3 cos, which we now know is cos 3 theta. I can now rearrange this into a very simple equation. It becomes the cos of 3 theta is a half. All right, cos 3 theta equals a half. That tells me 3 theta, pi on 3, 5 pi on 3, 7 pi on 3. Why did I bother with 3 answers? Normally we just go between 0 and 2 pi. Why did I give 3? Any ideas? Exactly. Remember when we did polynomials? And we said we won't have more solutions than the highest power. This is a cubic, so I know it's going to have 3 solutions. So I just need 3 consecutive solutions. Similar to what we saw with demands yesterday. We just needed to substitute in 3 consecutive numbers if it was cubed. I obviously chose the most basic one to start off with. I mean, it seems to be the logical one to do. Pi on 3. The next one would be in the 4th quadrant because cosine's positive. 5 pi on 3. Then I'm back into the 1st quadrant again. So I'll add 360 degrees or 2 pi to the first answer. 7 pi on 3. Divide each of those by 3. There are our 3 solutions to this equation. Well, not quite. That's what theta is. Theta was something I introduced to solve the problem. Remember, the actual answer is x. So the solution is cos pi on 9, cos 5 pi on 9, cos 7 pi on 9. So actually, I've given them all 3 solutions to this problem, but I've certainly shown that cos pi on 9 is one of those solutions. Still carrying on from that, now they want me to work out what this would be. Cos pi on 9 times cos 2 pi on 9 times cos 5 pi on 9. Again, it's going back to polynomials because we now have the 3 solutions or the 3 roots to the equation. So I know what the sum of the roots are, the product of the roots, 2 at a time, 3 at a time. That's what we're going to play around with. We need to get our question in terms of the roots. Pi on 9. Yep, that's all right. That's one of the roots. 2 pi on 9. Oh, that's a problem. Haven't got that one there. 5 pi on 9. Yep, that's there. So it's the 2 pi on 9 that's causing me the problem. And the root that I hadn't considered out of my list was 7 pi on 9. So somehow I need to change that 2 pi on 9 into a 7 pi on 9. Well, okay, so cos pi on 9, cos 5 pi on 9, and cos 7 pi on 9, we know are the roots of that equation. The product of the roots is 1/8. We know that the cos of pi on 9 times the cos of 5 pi on 9 times the cos of 7 pi on 9 would be 1/8. But 7 pi on 9, it's an obtuse angle. It's in the 2nd quadrant, so it's negative, and it's the same as the acute angle 2 pi on 9. So cos of 7 pi on 9 is the same as minus cos 2 pi on 9. So I can now say, well, cos pi on 9, cos 2 pi on 9, cos 5 pi on 9, they must be negative 1/8. This question, by the way, very common. I've seen it asked so many times in different assessment tasks over the years. Sometimes they give it to you, but a lot of times they ask you to prove it. So z equals cos theta plus I sine theta. You might not have to prove both, but we're going to do both. Z to the power n plus 1 on z to the n and z to the n minus 1 on z to the n. Okay. Well, z to the n, using Demar's theorem, will be cos n theta plus I sine n theta. 1 on z to the n, well, that's the same as z to the negative n. Again, using Demar's theorem, cos negative n theta plus I sine negative n theta. Now I'm going to use the odd and even function idea. Cos of minus n theta, cos is, as you said, even. So cos of minus n theta will become cos n theta. Sine is an odd function, so it will become minus sine n theta. So 1 on z to the n is cos n theta minus I sine n theta. Finding these two results now quite easy. I just got to add or subtract. So z to the n plus 1 z on z to the n, we end up with 2 lots of cos n theta. And when we do the subtraction one, we end up with 2i sine n theta. As I say, very common question asking you to prove it. However, if they do not ask you to prove it, it is certainly fine to quote it. Right? It is pretty much an accepted result. So if you need to use that idea to solve any problem, don't worry about proving it unless they ask you to. You can just quote it and say, well, z to the n plus 1 on z to the n is 2 cos n theta, and similarly for the sine one. Well, how do we use it? Okay, back to trig identities. Express cos cubed, but I want it all in terms of cos of some multiple of theta. Cos cubed is what I want. Now, the trick is to go to cos theta rather than cos theta, because the relationship I know is that z plus 1 on z, so where n is 1, is 2 cos theta. So I'm going to expand out the z plus 1 on z all cubed. So 8 cos cubed will be z cubed plus 3z plus 3 on z plus 1 on z cubed. And this is where the symmetry of those expansions works out very nicely for us. Because if I group all the things that have a coefficient of 1 and all the things that have a coefficient of 3, so I have z cubed plus 1 on z cubed, back to my theorem. Well, that's 2 cos 3 theta. And I have z plus 1 on z. Well, that's 2 cos theta. So I now can say, well, look, 8 cos cubed theta is 2 cos 3 theta plus 6 cos theta. I just got to divide by 8 and I've got my result. So we get 1/4 cos 3 theta plus 3/4 cos theta. So again, using complex numbers to actually solve this problem is so much quicker than when we were playing with trig identities before. All right, have a go at some of those. 7B out of our fake Cambridge. There we go.